All right, the unofficial title of Chapter 6.8 is Integrals to Infinity. The official title is Improper Integration because integrals, when we define them initially, have to have a finite start point and finite stop point. So going all the way to infinity is kind of improper, but they're really important to be, it's really important to be able to do that. So a quick overview, we're skipping Chapter 6.7 because most people did that in Calc 1. And there's really only one big fact we need from Chapter 6.7, which is this limit. So we've got t to the p, like t growing kind of like a polynomial, t squared, t cubed, for example. So that's growing, and then e to the negative at is decaying exponentially. And so which one wins, the polynomial growth or the exponential decay? And L'Hopital's rule helps us figure out that exponential decay always wins against polynomial growth. So here's a few different pictures for like t to the negative 1, t to the 0, t to the 1, t to the 2, t to the 3. And polynomial growth starts winning initially right out of the origin, but then exponential decay takes over and the whole thing just goes to 0 as t goes to infinity. So that's something that we won't want to have to rederive every time. We will just be able to say, oh, we came up against this again, and we know that that value is 0. We'll be using other common function limits, like what's the limit of log x as x goes to infinity? What's the limit of sine x as x goes to infinity? Some of these don't even exist. And so I have an organizer sheet that's about common function limits that we'll be referring to throughout Chapter 6.8. Then we have a Chapter 6.8 warm-up assignment that you should do before watching the videos for Part 1 and Part 2. And then I'm dividing the homework into Part 1 and Part 2. The book doesn't officially say, here's Part 1, here's Part 2, but here's the breakdown. In Part 1, we'll be doing integrals with an upper end of infinity, or a beginning point of negative infinity, or even starting at negative infinity, going all the way to positive infinity. And then we'll also be doing integrals where the function has a vertical asymptote, so the function value itself goes to infinity somewhere between where you start and stop. And then in Part 2, we'll be looking at, can we come up with some general rules for saying when these integrals are equal to 0 or some finite value, or the integral itself is infinity. So here's the names of some of the things we'll be doing in Part 2. Let's take a look at the warm-up thing. Oops, I meant the common function limits thing. All right, here in our big homework file, I've given us a reminder of that big result from Chapter 6.7 that we'll be using a lot. And then here's the organizer. It's a big table where the idea is you sketch the function that's given to you, and then say what's the limit as x goes to minus infinity, so the limit toward the left. What's the limit at 0? And usually here we care more about coming towards 0 from the positive side, like from the first quadrant kind of. So that's what this 0 plus means. It means limit from the right as we move toward the left towards x equals 0. And then what's the limit all the way to the right as x goes to infinity? So you should print this out. Probably, I think it all fits on one page, and do each sketch and say what the limit is. And then in the next section of the homework file here, I have the solution key, but you might think, well, why should I bother thinking about each one individually? Thinking about it and then checking the answer key is actually better for your learning. It kind of primes your brain to say, okay, I struggled on this, I know I need to know it, and then when you see the answers and reason about the answers, you actually remember it better than if you just read over the sheet and say, oh yeah, I knew all that stuff. I haven't found a wonderful way to fill in these sketches yet, so let me show you that on a piece of paper. All right, here's my lovely sketches. So x squared, obviously our favorite parabola. X to the 1, that's just y equals x. Square root of x actually has an infinite slope here at the origin because it's a kind of a sideways parabola. The parabola has a 0 slope at the origin. So the flat tangent line here becomes a perfectly vertical tangent line here. But its value is still 0. And then the curve just goes to infinity as you get larger and larger x. Here's x to the negative 1, that's 1 over x. X to the negative 2 by I looks a lot like x to the negative 1, except you're basically squaring x and then doing 1 over, so all the negative values give you positive y values. It looks asymmetric here because I'm not the world's best artist, but it really is symmetric. And then what I left out here that's actually in the electronic version is how about like x to the 0.1 or x to the negative 0.1 or x to the 1.1. So we'll go take a look at those on Desmos in just a sec. Then we've got exponential growth, exponential decay, growth and decay. Log goes to infinity to the right, but very slowly, and to negative infinity as you get towards 0, but also very slowly. Sine obviously looks like that, and cosine, you don't need my help for those. Arctan has horizontal asymptotes to the left and right. And then these two curves are called logistic curves, and they're really useful in a bunch of statistics and machine learning. They're both called logistic, even though one is kind of falling off and the other one is growing. It's obviously just a minus sign here, but they're both called logistic. And then surge curves, which we've used before. That's the thing that L'Hopital's rule from chapter 6.7 was telling us about the limit as x goes to infinity. All right, let's go look at x to the 1.1, etc. in Desmos. All right, here I have just plain x to the p, with p being a slider. Right now I've got p set to 1, so it's x to the 1, or y equals x. No big surprise if I set p to 2, then we get a parabola, or if I set p to 3, we get a cubic. What if I set p to just a little bit above 1? Here we go. So at 1, we just got a straight line. If p is slightly greater than 1, we get a slight curve here. It's kind of getting towards being a parabola, but it's not quite, but it does have a slight curve upward. What if p is slightly less than 1? It's actually kind of hard to see what's going on there. Let's bring it down to p equals 0.5-ish. So that's square root, and that's going off to infinity to the right here. What if p was pretty close to 0 but not quite 0? Then it's kind of a more severe version of square root. Or you could say, like if I did p to the 4th, that's p to the 4th is like a parabola but with a really flat bottom. P to the 1/4 approximately is like that turned sideways, so it has a really flat, what would have been a flat bottom this way is now this way. And then it's growing even more slowly than square root, but eventually it will get, once you get to infinity, it'll get to infinity. It's growing to infinity. So for p-values between 0 and 1, it's all kind of square rootish, you could say, all that same general shape, all concave down, and all goes to infinity. And then once you get below 0, here's p being -1. So that's everyone's favorite 1/x hyperbola. And then if I change p to be still negative but not closer to 0, it still kind of looks like 1/x. And then same thing for p being between -1 and -2. So the big domains where it looks basically the same are any negative value for the power looks pretty much the same. Any value between 0 and 1 looks kind of like square root, and then any value above 1 looks pretty much like a parabola, with 1 being the straight line. Right, so that's an overview of different non-integer p powers. I'm mentioning these because in calculus we don't usually use fractional powers unless it's a half. But in statistics, it's really common to fit a model and get just whatever the best fit value was, and there's no reason that has to be an integer or a nice half kind of number. So it's good to think of all these different ones. One fun thing we can do in Desmos here is say p is actually a list from like -2, well, let's go 0, 0.1, comma, 2, and then it shows the curves for all those p's all at once. We could even, so p equals 0 is this horizontal line. We're really only caring about the positive half here. So sometimes when p is less than 1, we get a concave down function. When p is greater than 1, we get a concave up function. All right, on to more 6.8 in the next video.